Hello and thank you for attending. I'll be presenting a project named PowerSpy, which is a joint work with Gabi Nakibly from Rafael Institute, Aaron Schulman and Gunaa, Veerapandian, and my advisor Dan Boneh from Stanford University. So let's start. The project deals with the location tracking using analysis of power consumption on the mobile device. So as we know, as we can notice nowadays, modern smartphones have many sensors, and some of them are pretty well understood, as well as their privacy implications. Some of them possess obvious privacy risks. For example, a microphone can leak sensitive audio information. A camera is obviously sensitive, and some of them are protected. I cannot list all the prior work on privacy and leakage and side channel attacks on different sensors. So there are some that are uncontrolled, that are unprotected, and there are interesting side channel attacks, for example, infrared location using accelerometers, attacking the microphone and ambient sound recognition. And there's an interesting localization attack using the speaker on-off status, very interesting. So, and there's much more work. And I want to talk about a lesser known sensor, which is completely unprotected now. So for example, if you look at an application that requires an access to the GPS, a conscious user would obviously notice that upon installation of the application and understand that it can reveal his location, so it possesses a privacy risk. Even coarse location indicators such as signal strength and cellular network information. And there is another sensor that's completely unprotected. Any application can access it by accessing those paths, those files in the sysfs, voltage now and current now, and by reading from those files to get a power measurement for that moment. So with a pretty high resolution and pretty high frequency, up to 100 Hertz. And basically, the user, upon installation of such an application that has access to it, doesn't see anything. He sees that it requires no permissions. And it exists in the recent versions of the phones. And even if you don't have access to current now, I can talk about other methods that can bridge this gap, but let's move forward. So what we show is that power meter reveals location. And let's look at the method, how it can be done. So I want to talk a bit about the threat model, about the attack model. What I would like to do as an attacker is to install some application that is seemingly innocent on your mobile device. And this application would start, as we've seen before, it has access to those files, and it can start gathering power consumption information, power consumption samples. And by either linking them to a remote machine that runs our algorithms, or by running the algorithms on the mobile device itself, it can now start tracking the user and reveal his past location, or as we show, track him in real time along a certain path. And I'll define the specific attacks later on. So let's look at this animation. We have some vehicle that's close to the transmitting antenna, a user with a mobile device in the vehicle. Let's look at it again. So when the car is close to the transmitting cellular antenna, the reception is good. And then as we get further away, the signal becomes worse because we're farther from the source of transmission. And then if we have obstacles between us and the antenna, the transmission the signal degrades, and the channel quality is even lower. So basically, signal strength depends on a couple of parameters related to location and environment. So location is how close you are to the source of transmission, and environment is the obstacle between you and the transmitting antenna. Okay, and these are pretty constant factors. So along a certain route, they wouldn't change much with time. And we wanted to verify this thing, although it was shown in previous work. So we drove on 2 different days along the same route, and we plot the signal strengths corresponding to different locations. And as we can see, there is barely any difference between the 2 plots. So the signal strength is pretty stable over time. Okay. we also have the next observation that power consumption is somewhat a function of the signal strength. So despite many other factors on the mobile device that can affect power consumption, such as application running, you turn on the GPS, you turn off the GPS, you play music, it's still a major factor. And it goes like this. So if you transmit under a low SNR, under bad channel quality, you have to compensate for this bad channel quality and put more energy into the transmission to compensate for it. And also on the receiving side, you put some effort into signal amplification and error correction. So even not only the baseband chip, but other units might be consuming more power. And it was also verified. This link was, the dominance of this factor was verified experimentally before. So we also wanted to test that a bit before we proceed. So first we wanted to understand how stable and how consistent it is across different devices. So on the left we see measurements from two different mobile devices of the same model while we were taking the same route. And they're not synchronized in any way. And we can see that there is a very high correspondence between those graphs. We can see that the peaks are pretty well aligned. So perhaps we can infer some information from some base measurement and predict what would be the power consumption on another device that is taking the same route. We also wanted to check how it works for different phone models. So on the right we have two Nexus, they're both Nexus devices, one is 4 and one is 5, but actually those devices have a different baseband chip. So in terms of the communication circuitry, they're somewhat different, and we still see a pretty high correspondence. So not as good as on the left side, but it's still very significant. Okay, so that's encouraging. What can we achieve with that? So we defined three main goals. The first one is route distinguishability. What we would like to do is to determine the route taken by user from a given set of routes. And this enables us to infer the previous location of the users, and for example, tell whether the user on a certain day took one highway or the other to work, or where else has the user been driving. And you can think about various applications, and obvious one would be something like advertisement, where even a small advantage in guessing such a thing would give you value, and you can think about more malicious or better applications. The second goal is real-time tracking. So what we would like to do is we know, or we assume that the user is taking a certain route, and we would like to tell where on this route the user is. And once we log down on this target, we want to keep tracking it along this route in real time. So we receive samples from our application that reads power consumption on the mobile device in real time. We accumulate those samples, and we want to track the user. The third goal is learning new routes, new route inference. So this is beneficial for a setting like a city grid, a city mesh, where we have many small road segments connecting many intersections. So there, the possibilities for creating different routes are vast, and in order to create a reference set, we would need to drive along too many routes. So what we would like to do is to perform work that is linear in the number of those short road segments. And by work, I mean driving along those short segments and measuring the power profiles corresponding to them, but still be able to infer all the possible routes that you can compose using those segments. Okay, so that's the hardest task of all. I'll talk a bit about the technique that's in the heart of our algorithms. So we refer to each power profile as a time series. We have a series of samples that correspond to power consumption, different times along the route and different locations along the route. And what we would like to do is having some base measurement for which we also know the reference locations to be able to compare it to another target reference which is unlabeled, for which we don't know the corresponding locations. So it becomes a problem of comparing time series. And what we use is a known method called dynamic time warping for this kind of comparison. And we would like to build a classifier at least for the first goal. It's a classification task. So we would like a classifier that's built that's based on some similarity metric defined by this algorithm of dynamic time warping. And the time warping is needed. It's important because on one day, under certain traffic conditions, I can drive along a certain route at a certain speed, and the other day the user is taking this route and driving at a completely different speed due to traffic or stuff like that. So the user might spend more time at some point, and some features in the graph might be shifted. Some of them may be compressed. The offsets might not be the same. So this is why this time warping is very important. And the time warping works like this. So instead of matching the samples one-to-one, the regular Euclidean metric, we're looking for some optimal matching between the samples. So every human can see that those graphs on the right, they're kind of similar, but for a machine, we need this specific algorithm to find this better matching of the samples that would give us a more meaningful similarity. And here we show what we can do with it. So we see on the left sequences that are obviously related to each other. They're pretty similar. It's kind of the same. The power profiles corresponding to the same routes, but they're not aligned. And on the right, we apply this dynamic time warping, and we align those sequences, and you can see. Then you can clearly see how similar they are and calculate a meaningful similarity. Some data preprocessing we perform. So first of all, we apply DC offset removal and normalization. So this is important for the following reason. For example, an application that's running in the background, such as a GPS, can introduce a constant shift in the power consumption. So the power consumption is higher, but it is higher by a constant additive factor. So what we would like to do is to get rid of this offset to be able to compare time series that were measured under different conditions. And that's why we use this normalization and offset removal. And we also compensate for gain difference, which might be introduced by different amplifiers in two different devices to normalize the amplitude. The next step is some smoothing. We're not interested in the short-term noise in the power profile. The power profile, as you can see, is very noisy. We're interested more in the general trends, so that's why we perform this smoothing using a moving average filter. And we're also don't really need this high-frequency sampling that we can get from the sensor. So we perform downsampling, and that can be important for improving the computational efficiency of our algorithms and to compare less samples. So that's kind of an important step too. Let's look at the results of evaluating those algorithms. So for the first goal, we performed many experiments, and there are several results here for different numbers of unique routes. So the more unique routes you have, obviously the classification task becomes harder. And what I would like is to focus on the highlighted results. So we have relatively a limited number of unique routes, but that can be interesting for some user that you're aware of her routine, and you kind of know what are the possibilities for this user to where she usually drives, and you want to track this user. And the success rate is pretty high there, and it can be improved further. As we increase the number of unique routes, the success rate goes down, but it's still much better than a random guess. So there is a significant information leakage through this side channel. Let's talk about the real-time tracking. So again, we receive a window, we accumulate a window of samples, and we would like to track a user along a certain route. So for that, we use a variant of dynamic time warping called subsequence DTW to determine the offset of this subsequence of samples we received in the larger reference profile. And according to this offset and the corresponding coordinates we know for it, we can infer the current location of the user. So that's an animation based on some real data we recorded. So you can see that we quite successfully can track the vehicle along the road. The vehicle represents the true location, and this target the estimate. And you see that towards the end we have some error, like we jump ahead. So I'll talk about those errors in a second. Let's look at a couple of graphs. So the middle graph represents the error in time, the estimation error. And on the right, we see a histogram of errors. So we can see that most of the errors, according to the histogram, are concentrated in the low values, up to like 500 meters, most of them. Some of them are a bit higher, but mostly the tracking seems pretty good. And you can notice this peak, this spike in the error graph towards the end. And if you look at the animation, so the red dot represents the estimate, and towards the end it's completely off the true value. So that causes this big spike. And what we can do with such an obvious error is to apply simple logic. So if there is a car that's driving along a route, it cannot suddenly be back on this route by 2 kilometers or something like that. So we can apply this simple, very trivial motion model and get rid of this error spike. So yeah, that's how it looks like after. As we can see, we still have those this bump here, so the error goes up, and we would like to improve upon that as well. We tried an algorithm that's called optimal subsequence bijection. And it is closely related to dynamic time warping, but it assumes that both the reference and the target profiles can be noisy. So instead of referring to one of them as kind of a ground truth, and not dropping any samples from it, it allows dropping some samples. So the intuition is it kind of can compensate for this noise in the measurement. And we tested it. We applied it to a couple of different profiles we collected, and we can see that in most of the cases, most of the time, the optimal subsequence bijection indeed outperforms the estimation using the dynamic time warping. Yeah, so sometimes dynamic time warping for short periods performed better, but mostly this method seems superior. And this is how the tracking looks using optimal subsequence bijection, and you can see that it's indeed better. So the estimate seems more consistent with the ground truth. Okay, let's proceed to the third goal, which is the new route inference. So we want to take those short road segments, measure the corresponding power profiles, and infer new routes that we didn't drive along before that. What we do is we take the intersection in the city, in the dense area, and we refer to them as nodes in a graph. And to the road segments connecting those intersections, we refer to as the edges that connect those nodes in the graph. And this motion of the user is basically now some traversal of this graph, so some hopping between different states that can be connected or not connected according to whether they're connected in reality by those road segments. And what we'd like to do is having our observations, the data we have, to infer and learn the past hidden states in this model. So it becomes a kind of a probabilistic graphical model of location of the user. And we would like to apply some graph inference algorithms to learn those past states. So there are all kinds of possibilities. We ended up implementing a particle filter because that allowed us to sparsely sample a large amount of hidden states we have. And I'll present some. So the evaluation was done in this area. It's not like a huge number of intersections, but you still can compose quite many different routes here. And I'll just present some qualitative results just to illustrate this thing. So I won't go into the metric, but you can see that we can recover a significant portion of the route. And if you remember the map, again, you can have many more guesses. So it's pretty good. It's very significant compared to what a random guess would yield. So for example, on the left, you see that we kind of recovered most of the route, and then we missed one section. The green is the real route taken, and the red on top of it is what our estimate was. Here again, we recover a significant portion, like 3/5 of it, and then we missed 2 sections. Okay, so that was kind of the hardest task, and still there is a significant advantage. Okay, so let's move on. Let's see what can be done further. It would be nice, it would be great to collect a big data set of power profiles for US routes. And it's not so hard actually. So every application that is widespread today and has access to location can start collecting and building such a database by starting to record those power measurements, aggregating them, and also aggregating the corresponding GPS locations. So with that, you can start building such a reference, and whoever builds such a database will, as we show, get those GPS-like capabilities without really accessing any location information. And the next one would be to improve on this hardest task I mentioned of new route inference. So since it's a graphical model, we would like to apply algorithms like Viterbi, more sophisticated algorithms than what we did, and improve the results. I want to also add a future warning. So HTML5 apparently exposes API for accessing the battery charge level. And that's a very coarse indicator. So the derivative of that would be the power consumption, but it's a very coarse power consumption. I don't believe anything can be done with it now, but it should be kept coarse. Otherwise, it would expose you to this attack through a web. Let's talk about possible defenses, and first of all, things that would not defend. So adding noise, this defense would require adding the amount of noise that would basically yield the power measurement inefficient for any legit use of actually profiling your application, because we anyway smooth the noise and look at the general trends. And also limiting the power sampling rate. We downsampled the samples, so it would just save us a preprocessing step. So that wouldn't help as well. What would actually help is excluding possibly the TXR exchange from the power consumption measurement, because many times you're just interested in profiling your application and the CPU effort. So excluding that would decouple the energy that goes into transmission. Include the power consumption as a coarse location indicator in the same way that signal strength and cell ID information is included today. And also provide abstractions instead of the access to the raw data, although this one is kind of hard. You need to understand what are the useful abstractions for a user. The conclusion is that sensors can have unintended consequences, and that power meter access should be restricted. And we need to apply the permissions that we have for other obviously dangerous sensors to this sensor as well. Thank you, and I'll take questions.
I'm Pei Wang from Penn State. I actually have 2 questions. The first one is, how exactly do you get the current and voltage values from Android? Correct me if I'm wrong, but according to my experience, it's really device dependent. Depends on what kind of gouging chips they're using. And like several years ago, I am doing some related work on this. And I have 2 phones, one from HTC and one from Samsung. And Samsung, the phone actually doesn't allow me to do that.
Mm-hmm. So you are right. Several years ago, you would have a lot of trouble getting those measurements. The new models seem to introduce it, but for example, like a Samsung Galaxy S3 device still doesn't expose the current meter. So it's a problem. Yeah. So we worked with mainly with Nexus devices, HTC Desire, which have this. But the tendency is to introduce those current meters. There's apparently a strong incentive, and we got feedback about that. So because there is a lot of interest in this profiling that it enables, and also there are methods that would allow you to. There's prior work on how you can infer the current according to only voltage, by reading only the voltage, some fluctuations in the voltage. So that's pretty involved. We didn't go into that, but there are methods that exist for that as well. So by applying them, you would be able to probably infer power consumption as well, only having the voltmeter, which is present on most of the phones.
Okay, so the next question is, so you are actually measuring the overall consumption of the phone.
Yes.
And actually the data which interests you is only the power consumption of probably the radio.
Yes.
So I see you you assume the background consumption is a constant, and you remove that from the raw sample data. Have you validated that consumption is true? Because there are some publications on power consumption measurement on Android, like in 2013 in SDI and 2014 in Census. Their study seems to suggest that the background is actually very noisy.
So yeah, the background is, it would be fair to assume the background is noisy. That's why I thought about the idea. For example, I was kind of skeptical because until we started testing it. So we don't assume anything. We don't subtract something that we pre-measure about different applications. We just standardize it by removing the mean of the measurement. So, and apparently there's still enough information. So it just that's what the experiments show.
So for example, have you tried when the person is listening to the MP3 audios and carry the phones, walk around?
So we tried it. We did the experiments under different conditions. Mostly, of course, at this stage, we wanted to focus on less noisy phones, but we also performed measurements when the music was playing, when the GPS was on. So the GPS is not a problem at all because it raises the power consumption, but it just becomes a constant factor, and this method, the dynamic time warping with our normalization, copes with it well. But yeah, if you have more noisy phones, especially for the new route inference, where this prediction, this correlation between short segments is very sensitive, so there it definitely degrades the results. Yeah, it's true.
Thanks.
Hi, my name is Anjan from ETH Zurich. How much, the question is, how much does an attacker need to know about the target? Like, for example, do I need to know what kind of applications is a person actually using on his mobile phone? For example, when I profile a particular route, I might be using Facebook installed in my phone, but maybe the actual user does not have Facebook installed, or maybe the push notifications is turned on in the actual user, but when I profile, I don't have push notifications turned on. So how much knowledge would you need to actually have high accuracy here? Yeah,
so what I could suggest at this point, it's to really answer that, you need to collect a bigger data set under different conditions. What I would suggest is, so for example, the metric we apply is it basically becomes nearest neighbor because one nearest neighbor because we have multiple reference profile and the dynamic time warping that yields the best correlation. That's the one we take. But if we measure a couple of profiles under different conditions, then we would have a sufficient set where we'll have a best matching reference profile for this particular condition.
Did you try some different configurations of applications?
So we tried different fonts. For example, some of them were kind of out of the factory. Some of them were heavily used previously by users.
I'm talking about the application level. I mean, if, for example, when you are profiling, if there is an incoming call, the power consumption probably goes higher. Okay,
so the incoming call, for example, I can show you this thing. That's how an incoming call looks in the power profile. So that's something that you can easily eliminate. Okay, that's an easily recognizable feature. So those interruptions, we can cope with them. Something like transmission, that only helps us because that actually strengthens the effects of the transmission on the overall power consumption. So that's actually would be great.
Thanks.
Xu from Zhejiang University. Excuse me. Very interesting work. So I assume that the profiling works because you assume that all the cell towers location does not change. Well, that's mostly true. I know that some carriers try to save energy, so at night, at midnight, they may turn off cell towers. So my question is, will the time of day affect the accuracy of profiling?
Yeah, I believe it's true, and for additional reasons as well. For example, traffic will change. So while we cope with the different traffic profiles in this manner I mentioned, it still would be beneficial to measure reference profiles in several points along the day and take the best matching to the current conditions. So yeah, definitely, if you have more references for different conditions, even things like weather can influence. For example, humidity can influence the channel quality. So even those conditions, it would be great to have matching reference profiles for them. Yeah.
Thanks.
Joe Zipkin, MIT Lincoln Laboratory. Following up somewhat on the previous questions, how robust do you expect this to be to realistic variations in pattern of life? For example, if halfway through my route I stop and get gas, and for a while the signal strength is different from how it would be if I'd continued going. If I check my email or don't while I'm stopped for gas, if I plug my phone in or don't during my trip.
Mm-hmm. So I hope you don't check your email when you're driving, but
no, when you're stopped at the gas station. Of course.
yeah, when you stop at the gas. So that I guess would be actually an easier one because there would be kind of a clear feature. For a while you'll have a similar power, you have like a constant power consumption, or if you start checking stuff, that would introduce some problems. So it depends on how distinct are the other features that this dynamic time warping can use as reference and to fix it. So for that you just need to test. Yeah, we didn't test it so extensively, but if you combine it with additional side channels, for example, accelerometers and gyroscopes are completely unprotected nowadays as well. So using that, you could. There are other works there are works that we cite that deal with understanding what is the kind of motion pattern of the user, whether he's driving or he's static. So you could combine it with that and get those answers.
Have you done any work fusing these features together with things from the accelerometers and others like you were saying?
No, so actually not. At this point, what we wanted is just to show the information leakage, how much information leaks through this one. So we avoided it actually.
Thank you.
Thank you.